Alrighty, gang, welcome back to Calc 1 Honors. Today we're going to push forward, starting to learn about applications of the derivative. So today I'll be showing you some of the things in detail that William kind of previewed for us yesterday as a little segue into 4.1. Let me turn on the screen share. We can get moving. And let's bring up the book. Oops, excuse me. All right. So today we're going to talk about the mean value theorem, and given time, I think there will be, we're going to talk a little bit about how derivatives affect the shape of the graph. And I may add, let's see, so in your current homework, I actually just put 4.1 stuff, and I intended to put 4.1 and 4.2 stuff in there. So what I think I'll probably do is kind of give you an extra little homework set, something to work on starting today that has some 4.2 and 4.3 stuff. All right, here we go. So this is MAC 2311. The section number is OH1, which means this is Calc 1 Honors. And today is the 15th of October, 2021. Today we're going to talk about the mean value theorem. Which is section 4.2, and a little bit on how derivatives affect the shape of the graph. From section 4.3. So the mean value theorem is something that that in the syllabus, I think I have pushed back after we visit this twice. We talk about the mean value theorem once now, and then once again when we finish talking about integrals. And I think it's possible, yeah, that we didn't actually list it here. I just say 4143, but I do want to share with you the mean value theorem. I'm not going to give you much in the way of homework problems on the mean value theorem. Those will come later. Where it actually shows up in the syllabus here, MVT, because there's two different versions of the mean value theorem, one for integrals and one for derivatives. And it's nice to be able to talk about both when you're actually solving the homework problems. So I'm just going to share with you the statement of the theorem and draw the picture, and I'll give you one or two little problems, but there's really not much we can do with it at this point that isn't very contrived. Okay. So the mean value theorem says this. If f is continuous on the closed bounded interval AB and differentiable on the open interval AB, then there is a number C between A and B such that f primed of C is equal to f of B minus f of A, all divided by B minus A. And the key to understanding this thing is to remember what the right-hand side there is. F of B minus f of A divided by B minus A, that's a slope. That's the slope of the secant line joining the points A comma f of A and B comma f of B. So kind of the intuitive interpretation of the mean value theorem, let me draw you the picture, is that if you have a function which is sufficiently nice, let me say And here's A, and over here's B. So here's the point A comma f of A. Here's the point B comma f of B. This is the graph y equals f of x. And you look at the secant line. Which is this orange line here. Then there will be a parallel tangent line somewhere between A and B. And as I've drawn it here, I think there are two of them. So what we do is we imagine kind of skiing along this graph, and we ask, where is the tangent line going to be parallel to that secant line? And the two spots I see look to me to be like right here, and then maybe another one right here. So maybe I'll call this C1, and I'll call this C2. At both of these points here, the tangent is parallel to that orange secant. That's the idea. So if your function is continuous on the closed interval and differentiable on the open interval, then there will be at least one value of x between A and B where the tangent line is parallel to that secant line. That's what the mean value theorem says. The classic problem here is to find the c's, right? I give you a continuous and differentiable function and a specific interval a, b, and then you have to compute the slope of the secant line, compute f primed, and then find the value of c where that derivative is equal to the slope of that secant line. So let me show you one example like that, and I'll talk about a quick real-world application, and then we're going to move into section 4.3. We will, again, come back to mean value theorem after we've talked about integration a bit, because then we'll have some more context for it. So here's the classic problem. Let f of x be whatever you want. How about x squared plus 1? And find the number c guaranteed, I always misspell guaranteed, to exist by MVT, mean value theorem, for f on the interval, let's say -2 to +3. I can draw the graph of f of x really quick, and it's never a bad idea to do that. It's also important to verify or check that this thing is both continuous on the closed interval and differentiable on the open interval. Because f here is a polynomial, of course that's true. Polynomials are continuous and differentiable everywhere. So I'll call this -2, and I'll call this +3. So my secant line is going to be something like this. And I'm able to see, just by looking at it, that somewhere over here probably is that number c, right? Where I've got my parallel tangent. So our goal is to find this number c. We need two things. All right, what I'm going to be doing is trying to solve an equation like this. So I need to know what is this, and I need to know what is f primed. So here, f of b minus f of a divided by b minus a is f of 3 minus f of -2 divided by 3 minus -2. F of 3 is what you get when you plug 3 in here. So that's 3 squared plus 1 is 9 plus 1 is 10. Minus f of -2 is -2 squared plus 1 is 4 plus 1 is 5. And then 3 minus -2 is 3 plus 2 is 5. Oh, this is interesting. So this is 5 over 5, which is 1. That wasn't planned, but it worked out nicely. Also, f primed of x, the derivative of x squared plus 1 is 2x. So we're looking for a solution C to the equation 2x equals 1, right? F prime is equal to this ratio. And of course that means x is 1/2. So C equals 1/2 is our guy. Is the number MVT. Not bad, right? Pretty simple stuff.
Question.
Yes.
Did you say before in the beginning that that there's like two tangent lines, but like in this situation, is it possible that there's two tangent lines that are parallel to the
Yeah, good
secant?
question. So first, the mean value theorem guarantees the existence of one such number, right? There's at least one number C such that blah, 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 blah. As I drew this picture, there were two, and it's certainly possible that there's 2 or 3 or 10 such numbers. For this particular function on this particular interval, there is only one, right? So you compute this number, the slope of the secant line, you compute the derivative, and then you set that derivative equal to the slope of the secant line. That equation, in theory, could have many solutions. But for this particular function and this particular secant line, there's only one. Does that answer the question? You feel comfy with that?
Yeah, that's good. That's better.
Cool. All right. You can imagine if I were to take like a degree 3 polynomial, something that has a sort of S-curvy shape, that as long as my interval is wide enough to capture both hills of that S-curve, then we could end up with multiple solutions there, or definitely trigonometric functions. Lots of functions could have more than one. The picture here, Rolle's theorem is a silly special case of the mean value theorem. Picture here is like this, right? So at least one point must exist, but there could be multiple like this. The proof, we'll talk about that when we prove the second version of the mean value theorem. The example, the real world example that I'd like to describe for you is just something I'm going to talk through. It's not a problem to solve. It's just a fun thing to think about. It turns out to be the case, actually. It's convenient because Orlando's about 100 miles away from Gainesville, right? So tomorrow I'm driving down to Orlando. My wife's birthday is coming up and we're going to go down to Islands of Adventure. Have a good time to celebrate with her. If a cop makes note of me leaving Gainesville at noon and radios that down to another cop in Orlando who sees me arriving at 1 p.m., even if I'm not speeding at either of the moments those police see me, that second cop could issue me a ticket. How does the mean value theorem explain that?
The notion, because if, let's say, the speed limit is 75 miles an hour and you traveled 100 miles in an hour, just because the instantaneous you were doing, say, 60, does not mean that you weren't doing 140 in the middle.
Right. In fact, what we could say for sure So I will go ahead and write this down. So Orlando's 100 miles from Gainesville. If a police officer sees me leave Gainesville at 12 o'clock p.m. and another cop officer sees me arrive at Orlando at 1 o'clock p.m. Can the second officer give me a ticket? And the answer here comes from the mean value theorem. So my average velocity from 12 p.m. to 1 p.m. is 100 miles divided by 1 hour, which is 100 miles per hour. Therefore, by the mean value theorem, at least, I know it looks weird, at least one time t equals c, my actual velocity must have been 100 miles per hour. That's the idea. So your average velocity is like the slope of your position function. And your actual velocity is the derivative of that position function. So by the mean value theorem, since my f of b minus f of a over b minus a is 100 miles over 1 hour, or 100 miles per hour, there must have been at least one time, one moment, where my actual velocity was equal to 100 miles an hour. This is the slope of the secant line, and my actual velocity is the slope of the tangent line. So let me draw for you a possible graph here for S, my position. And here's my t-axis. Here's 1 hour. And over here is, of course, 0. Maybe I start off going slow. And if I'm going to arrive over here, I'm probably going to arrive going slow also. But in order to join these two by a smooth curve, there has to be at least one place where my tangent line is parallel to this secant line. And so at that time, maybe it's here. At that time, I had to have been going 100 miles an hour by the mean value theorem. Pretty cool stuff, right? I think this is a cutesy example, but it's 100% valid as long as my position function is continuous and differentiable. The continuity isn't a problem. Position is always a continuous function of time. I do not teleport. But the differentiability, then that's maybe arguable whether your position function is actually differentiable. Yeah, the joke there is that on I-95 or even 75, maybe even some parts of the turnpike, I would be going too slow if I were going 100 miles an hour, or at least barely keeping up with traffic. But yeah, that's the idea, right? So if your position function is smooth, then any average velocity has to be attained at some point. You cannot travel at a certain average speed without at some point going that exact speed, which I think is a neat example. So what we've shown here is that V of C, which would be S primed of C, equals 100. So yes, the cop, if he knows calculus, or she knows calculus, could issue me a ticket. Despite never seeing me speed. Okay, I think that's enough on the mean value theorem for today. The only problems I'm going to ask you to solve regarding these right now are the, find the number C guaranteed to exist by the mean value theorem. And I'll give you more problems that are a little bit deeper when we get into the mean value theorem and for integrals, which we'll do later in the semester. What I do want to talk about today in a little more detail is how derivatives affect the shape of the graph. So some of these things are things that we talked about on Wednesday. This should be a capital G, which is section 4.3. This is an important section. This section, together with 4.5, summary of curve sketching, these are probably the two most important sections in chapter 4. First, a theorem. If, let's say, let I be an interval if f primed is positive on I, then f is increasing on I. Also, if f primed is negative on I, then f is decreasing on I. And we did touch on this previously, but the picture I think is sufficient to convince most people. So here's my x-axis. This is the graph y equals f of x. And I'm just going to chop this up according to where the function is increasing and decreasing. And if we look at tangent lines, this we're increasing here, we are decreasing here, increasing here, and decreasing here. If I call those numbers A, B, and C, we are increasing from negative infinity up to A. We're decreasing from A to B. We're increasing from B to C and decreasing from C to infinity. And if you look at a tangent line anywhere in here, you'll see that the slope of that tangent is positive, which means f primed is positive. If you look at a tangent line anywhere in the decreasing interval here from A to B, the tangent line has a negative slope, so f prime would have to be negative. And the same is true at all these other guys, right? So up here, f prime is positive because that tangent line is positively sloped. And over here, f prime is negative because the tangent is negatively sloped. Now this does assume that f is differentiable. Right? If f is not differentiable, we cannot talk about the derivative. So we're assuming here that f is continuous and differentiable on the interval I. But as long as that's the case, this provides a good tool for hunting to find intervals of increase and decrease. Let's look at an example. Okay. So I'm going to write this down and we'll come back over. Find intervals of increase and decrease for f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5. Should be able to see now. Can we see this okay?
Yeah.
Okay, very good. All right, so according to this theorem, what we need to do, since this definitely is a differentiable function, it's a polynomial. Polynomials are differentiable everywhere. What we need to do is calculate the derivative and figure out where that derivative is positive and where that derivative is negative. So we want to find where f primed of x is greater than 0. This will tell me where we're increasing. And where f primed of x is less than 0, decreasing. You could solve these inequalities one at a time, or you can solve them both at the same time by making a number line that tracks the sign of f. And that's what I recommend. So let's go ahead and run through this. My derivative, f primed here, follows from the power rule. It's 12x cubed minus 12x squared minus 24x plus 0. I can factor a 12x out, and what's left is x squared minus x minus 2. X squared minus x minus 2 can be factored as x minus 2 times x plus 1. So when you're trying to find out where any polynomial is positive or negative, what you need to do is find the places where it can change sign. And remember, those are what we call critical numbers. So you're going to find your critical numbers by taking the derivative and factoring it. And then you'll place those critical numbers on a number line. And I like to label my number line. This is f primed. I have here -1, 0, and +2. These are the places where f primed is equal to 0. F primed is never undefined. So these are the only places where f prime can change sign. this chops my number line up into regions. And in each of those regions, f prime will either be positive or negative, because these are the
You just
only
test the
places
number.
where f prime can change sign. We can get there by testing. Yep, that's an option. You can use test points, but I think a better option, and it depends on how good your pre-calculus class was, if you know this, you can use the end behavior and the multiplicities of these factors to fill this in. So the end behavior for the polynomial 12x cubed minus 12x squared minus 24x comes from the lead term here. This is a degree 3 term, which is odd, and it has a positive lead coefficient. So I can take I'm not going to sketch the whole graph of f prime. Well, actually, maybe we will. F prime here, that term here having odd degree and positive lead coefficient means that the end behavior is like this. You guys remember graphing polynomials from pre-calculus? I can plot those roots here, -1, 0, and 2. And then since they're each multiplicity 1 roots, we're going to cross the x-axis at each of those. So here's the graph of f prime. It's actually really easy to come up with because f prime is easy to factor. But if you don't remember this multiplicity and end behavior business, you can test points. So I could, for example, over here test x equals -2 and see whether f prime is positive or negative there. What do we think is going to happen if I test x equals -2? Am I going to get a positive number or a negative number out of this?
Positive.
So look at the graph we just drew.
Oh, so it like in and itself is negative, but it is increasing. So are we just going with the negative?
Well, I'm asking a very
it's
specific question. So if I plug -2 into this derivative here, f prime, do I expect to get a positive number or a negative number out?
Negative.
And the answer is, yeah, we're going to get a negative number out. We can see it from the graph, right? Or from the end behavior. This function has to go down on the left, which means anywhere over here, anywhere to the left of that first root, the function has to be negative. But we can test a point. Let's go ahead and do it. So f primed of -2 would be 12 times -2 cubed, which is 12 times -8, minus 12 times -2 squared, which is 12 times minus 12 times 4, minus 24 times -2, which is plus 48. And this will come out to be negative if you do the computation. So 12 times 8, what is that? -96. -96 minus 48 is negative. Oops. My arithmetic skills are poor. And then we're going to add, oh, we're adding 48 back. That's -96. Right. So this is -96, which in particular is negative. All right. We could test a point from each of these regions, but I really don't recommend that. So what we need to do is think back to our pre-calculus class and remember how the multiplicity of a factor affects the sign of the function. This guy, -1, is coming from this factor, which is an odd multiplicity, factor, which means we will change sign as we hop over it. So we go from negative to positive at -1, and that's what you see in the graph here. This guy, x, is also a multiplicity 1 factor. Since that multiplicity is odd, we will again change sign as we hop over it. So we'll go from positive back to negative. And then finally, 2, this critical number, comes from this factor, which is also multiplicity 1. So we will again change sign as we hop over that guy. So at most, you should be testing 1 point, right? If your derivative is a polynomial which you can factor, then you should have to test at most 1 point and then use multiplicities. Ideally, you would use the end behavior and the multiplicities and not even have to test a single point. This is something that if you do not remember this, you should go back and review the section on polynomial inequalities from your pre-calculus class. I can see, let me see if I have anything posted for you guys in the modules there. I don't believe I do. This is something that, well, maybe we do, maybe we do. Let me see. Let me see. Oh yeah, here it is. All right. So he's doing this with test points. Does he ever do this with multiplicities? No. All right. He's just doing it all with test points. That's a shame. And this allows me to answer Radha's question. What do you do if your derivative doesn't factor nicely? What do you do if it's a trig function, something like that, where there's no hope of factoring, or something involving gnarly square roots? Then you have to test points. So kind of the fundamental way to approach a nonlinear inequality is to make a number line, find the places where that thing can change signs, split your number line up into regions, and then test a point from each region. That will always work. But this trick of using multiplicities is nice. So let me so we've got inequalities and end behavior. That looks pretty good. That's polynomial functions. Yeah, something like this. All right, I'll take a look through these things and see which ones are best, and I'll post the best ones for you. So here we're testing points again, making sign charts. We're going to use multiplicity tricks using properties. Yes, very good. Okay. Test point method, stacking factors, multiplicities. Here we go. All right. This looks pretty good. So I'll post that to you guys for some review if you need it, because you don't want to burn time testing points if you don't have to.
Testing point is set some points and put it in the derivative to check the sign is negative or positive. And so that, okay.
Yep. So we would take one x value from each of these regions. Like here I tested 2. Between -1 and 0, I could test -1/2. Between 0 and 2, I could test +1. And to the right of 2, I could test any number bigger than 2, like 2.5 or 3 or 10. But you can see how that would be time consuming because you have to do a bunch of these computations. All right, so let's finish up here. I now know that my derivative is negative from -∞ to -1, positive from -1 to 0, negative from 0 to 2, and positive from 2 to infinity. So f primed is negative on -∞ to -1, unioned with 0 to 2, and f primed is positive on -1 to 0, unioned with 2 to infinity. Therefore, f is increasing on -1 to 0 and 2 to infinity, and f is decreasing on -∞ to -1 and 0 to 2. And you'll notice that I'm giving these answers as open intervals. There's a reason for that. When you solve a strict inequality, f prime is strictly less than 0, or f prime is strictly greater than 0 for a continuous function, that answer will always be an open interval. And you may have learned back in your pre-calculus class that intervals of increase and decrease are always given as open intervals of x values. The reason for that is, if you look right here at the place where we switch from being decreasing to increasing, or right here where we switch from increasing to decreasing, I wouldn't want to say that f is increasing here. That's not true. And I also wouldn't want to say that f is decreasing here. That's also not true. What is true is that f is briefly, just instantaneously, for that one moment, doing neither of those things. So these intervals of increase and decrease will always be open intervals of x values. And that's because they're associated with solutions to strict inequalities. All right. This brings us to the first derivative test. So this is the theorem. For local extrema. Remember, local means the same thing as relative. And extrema means mins or maxes. If I want to refer to all the mins and maxes for a function using a single word, that word is extrema. So this is a test that allows you to locate local mins and local maxes, or relative mins and relative maxes. Relative and local mean exactly the same thing. So there is no excluding from one, not the other. The subtlety here is that sometimes your homework doesn't like you to consider endpoints as local extrema. But that's wrong. It is. It's just by definition wrong. It's an error in the textbook. And there isn't much we can do with that. We just have to read the questions carefully in the homework. If on the test you were to tell me that an endpoint is a local min or local max, I would say you are right. And if you were to leave them off, I wouldn't argue with you point-wise, but I would make a little note saying this is also technically a local min or local max. All right, so what does this say? This says if f is differentiable, and I'm saying differentiable full stop, differentiable everywhere.
Excuse me, so the endpoint can be a local minimum or local maximum?
Yes, that is technically true. So an endpoint can be a min, local min or local max.
But for the book, it just said extra local the absolute local maximum and the local minimum is on the endpoint. So this is an error for the book.
Correct. Yeah, the book has an error, and it's a pretty common error. What they're trying to do is avoid confusing you with the derivative, because we cannot talk about the value of the derivative at an endpoint, because a derivative requires a two-sided limit, and you cannot do a two-sided limit at an endpoint. But if you just look at the definition of a local min or a local max, you'll see that those endpoints absolutely satisfy that definition. So yeah, the book has an error.
But I have a question for the book. Is that the endpoint cannot become a local maximum or local minimum? Is because for the point, it should be both sides, right side and the left side. When the x is approached to the c, at that time left side and the right side is less than the point f of c, so that they have absolute maximum, but it doesn't have and also the local maximum is both side, left side and the right side, the point is less than the f of c. but if it doesn't have one side, it's incorrect. It's not. It cannot be a local maximum or minimum.
So we have to be
This-
careful about our
This
definition.
circular definition, yes.
Right, we have to be careful with our definition. So we say that f of c is a local max if f of c is greater than f of x for any x value near c. Now, what does that mean when I say x is near c? It doesn't imply that you have to be able to look at both sides. But if you look here, they say in definition 2 and elsewhere, we say if something is true near C, we mean it must be true on some open interval containing the number C. So if you have an endpoint, like over here, then you cannot center an open interval at that point because there is nothing to the right. However, is this the largest y value anywhere nearby on that graph? Well, yes, it absolutely is, right? If you zoom in on that part of the graph, then this endpoint is the largest value anywhere nearby. So it depends on how you define the word near. And because they use this very narrow definition of the word near, saying it has to be true on some open interval containing C, then you could not apply, you can't look at an open interval containing that and say within the domain, but my point here is that you could still center an open interval at this endpoint. It's just that there wouldn't be any part of the graph to the right. So we don't necessarily need to have something over here to compare to. We would just say that, yeah, there is no part of the graph that is taller than this nearby. So that would satisfy the definition of a local max. Even if you say you have to be able to center that, you have to be able to center an open interval there, the definition still works. It's just that there's nothing to compare to on this side. And that's not a problem. It really isn't. But Stewart and some other books conflate these ideas. What's the nicest way to say this? They really want you to be able to say that local maxes and local mins are related to a property of the derivative, which is precisely what we're going to talk about here. But that's not necessary. It is overkill. They're being too narrow with their definition of this word near. Now, I'm not actually aware, let's see, of a place in the book where they argue that endpoints cannot be local mins. Let's see, do they try to make this argument? I don't think so. Yeah, no, they do not. But this isn't something I'm going to beat you up about. So what I want to make sure you guys can do is apply the theorems and get the results. If you want to side with the textbook and say that an endpoint cannot be a local max or min, I'm not going to take points off. But I want you to know that in the broader mathematical community, most mathematicians would disagree with that. Most mathematicians would say, as I'm saying, that an endpoint absolutely can be a local minimum or a local maximum. So it's a matter of opinion, and it comes down to how you choose to define the word near. But I don't want to get caught up in the quagmire there. There's no reason for us to get lost in that. Just read the questions carefully. And if a question tells you not to include endpoints as local mins or maxes, then don't list them. But be aware that most people would consider those as local mins or maxes.
So will this kind of questions show in the exams? I am already confused because I don't know how to answer this question for right now.
So I will be very particular with the way I word the questions on the test. I will tell you either yes, include endpoints, or no, do not include endpoints. There will be questions like that, but I will tell you specifically what to do.
It sounds good, thanks.
All right. So if f is a differentiable function and f prime changes from negative to positive at x equals c, then what does that mean? That means f went from decreasing to increasing, which means you had to have gone through some sort of a valley. So then there is a local min at x equals c. And differentiable here, again, I'm using as in a general term. The function needs to be differentiable, but it doesn't necessarily need to be differentiable at x equals c. So if c is a critical number, then remember it's possible that f prime is undefined there. So let me put a little asterisk here. And then we'll say also if f prime changes from positive to negative at x equals c, then f has a, and there is a local max at x equals c. So this is your first derivative test. And the picture that goes with this is fairly intuitive. I just want to highlight some of the weirder things that can happen. So of course, we can have a local min like this. We can have a local max like this. But we could also have a local min like this. So this is the graph of the original function, y equals f of x. And let me call these C1, C2, and C3. Since f goes from decreasing to increasing at C1, that means f prime goes from negative to positive. So f primed is negative over here. F primed is positive in here. F primed is negative here. And f primed is positive here. And the asterisk here is differentiable near C, but not necessarily at x equals c. So really what we just need is for the function to be differentiable like over here and over here. If we're not differentiable at this point, that's okay. As long as we're differentiable everywhere up to this point on some interval and everywhere up to this point on some interval, then we're good. The same sort of thing is happening over here, right? This function is not differentiable at C3, but it is differentiable just to the left of C3 and just to the right of C3. And this is precisely why the book sometimes gets picky about endpoints, because we cannot talk about the derivative changing sign at an endpoint. We can say, oh, well, the derivative is negative everywhere to the left of an endpoint, but I can't talk about whether the derivative is positive everywhere to the right of an endpoint. And because they want you to be able to use this test to find all local minima, that's why they get snickety about that stuff. All right, so this is the picture. Let's see how we use the thing. It's the same as what we did just a second ago, believe it or not. We're going to be doing precisely the same thing. We'll make a number line for the derivative. They also include this failure case here. So if your derivative does not change sign at C, then you don't have a min or a max, but we don't, that's included here just by omission. So let's do it. Yeah, they want us to find the mins and maxes for that guy that we just worked with. So for the function that we had a second ago, which was, can I read it through here? Not quite. So what was that function? 4x cubed minus, oh, sorry, 3x to the 4 minus 4x cubed minus 12x squared plus 5 from previous example. Okay. So we've seen already previously calculated f primed of x as 12x cubed minus 12x squared minus 24x, which factored as 12x times x minus 2 times x plus 1. And we made that number line, right? So over here was -1, 0, and +2. And we saw that f primed was negative to the left of -1, positive between -1 and 0, negative between 0 and 2, and positive to the right of 2. So my derivative f primed goes from negative to positive at -1. And there's a notation I like for this. I usually put like an arrow down for decreasing and an arrow up for increasing. Down for decreasing, up for increasing. And this helps me visualize what's going on. If I go from decreasing to increasing, then this has to be a local min. If I go from increasing to decreasing, this has to be a local max. And decreasing to increasing again, local min. Now, I'd also like to find the y values. I'd like to know what is the actual point where this local min exists. I know the x value is -1. So the local min at x equals -1 has min value f of -1. So if I plug -1 into this original function, that will tell me the y value of this min. That's going to be 3 times -1 to the 4 minus 12 times -1 squared. I'm sorry, minus 4. I was looking at the wrong thing. 4 times -1 cubed. Yeah, this guy's correct. Minus 4 times -1 cubed minus 12 times -1 squared plus 5, which is 3 plus 4 minus 12 plus 5, which is 7 minus 12 is -5, plus 5 is 0. So the local min here is at -1, and the y value there is 0. The max at x equals 0 has max value f of 0, the y value on the graph there. And f of 0, that's easy. That's just 5. No computation necessary. Finally, the min at x equals 2 has min value f of 2, which is 3 times 2 to the 4 minus 4 times 2 cubed minus 12 times 2 squared, plus 5, which is 2 to the 4 is 16. So this is 3 times 16. Minus 2 cubed is 8. So this is 4 times 8. Minus 12 times 4 plus 5. And let's see, can we crunch this out nicely? So 3 times 16, that's 48. Minus 4 times 8 is 32. Minus 12 times 4 is also 48. Plus 5. So the 48s go. And we have negative 32 plus 5, which is negative 27. So I found all the mins and maxes for this function and their min and max values. Let's take a look at the graph of this guy. So we claim to now know where he's increasing and decreasing, where he has mins and maxes, and exactly what those points are. So the ordered pair here, this min is at the ordered pair, the point -1, 0. This guy is at the point 0, 5. And this guy is at the point 2, negative 27. And if I look at the graph of this function in Desmos, x to the 4 minus 4x cubed minus 12x squared plus 5. Here we are, -1, 0. And that looks like a local min to me. 0, 5. And that looks like a local max, doesn't it? And then if we zoom out a little bit and go down, we'll find our other local min at 2, negative 27. Not too bad, right? What we're wanting to get to is a place where we can draw this graph, or indeed just about any graph, really accurately, with the increasing and decreasing correct, the local mins and maxes correct, all of the stuff that we care about when we look at graphs of functions labeled correctly. Now, any questions on how we found these points? Okay. So the next thing that we need to talk about is concavity. There basically are 4 basic kind of graph shapes. These are like this, like this, like this, let's see, we got increasing, increasing, coming down, and we need decreasing, coming down. Okay. This I would refer to as concave up, and it is also increasing. So this shape here, where you're kind of curling upwards, or if you imagine pouring water in this, it would sort of want to collect here. We call that concave up. This is decreasing and concave up. This would be definitely increasing. And we would call this shape concave down. And this guy right here would be decreasing, concave down. We can think of even the most complicated graphs we know as being pieces which are shaped like this, stitched together. And if you know whether a function is increasing or decreasing and concave up or concave down at any particular point or interval, then you can sketch a really nice looking graph. Each of these features, being increasing or decreasing and concave up or concave down, are related to the sign of the first and second derivative. So increasing would mean f prime, the first derivative is positive. Concave up, turns out, comes from the second derivative being positive. Decreasing, we know, is associated with the first derivative being negative. And concave up, again, is associated with the second derivative being positive. Increasing. So f prime is positive. Concave down here would mean f double prime is negative. Decreasing would mean f prime is negative, and concave down would mean f double prime is negative. Where does this come from? Why does having a second derivative being negative mean you're going to look either like this or like this? It has to do with thinking about the rate of change for the tangent lines themselves. So y is f prime prime's sign related to concavity.
I have a questions. I can understand why the f prime is greater than 0 or less than 0, but I cannot understand the f double prime. How does it greater than 0 or less than 0?
That's exactly what we want to look at here. So I'm just now going to answer this question. So let me assume, so suppose f prime of x is positive on the interval I, and f double prime of x is positive on the interval I. We know that f prime means we'll be increasing, right? This means f is increasing. If f double prime is positive, that means that f prime is increasing, right? F double prime is the derivative of f prime. So if f double prime is positive, that means f prime must be increasing. It's exactly the same logic, right? If your derivative is positive, you are increasing. Well, f double prime is the derivative of f prime. So what does it mean to say f prime is increasing? Which means that the slope of the tangent line to f of x is getting larger as we move to the right. So f double prime is the derivative of f prime. F prime tells you the slope of the tangent line to f. So if f double prime is positive, that means that the slope of the tangent line, which is f prime, must be increasing as you go from left to right. Let me just try to draw a graph that does this. So this will be the graph f of x. And let me just tick off a few x values here. Maybe my tangent line starts out horizontal. All right, I'll say here, my tangent line starts out horizontal. So I'm just going to draw in some tiny little tangent segments. I'll mark these as like 1, 2, 3, 4. If f double prime is positive, that means f prime is increasing, which means as I go left to right, the slope of the tangent line must be increasing. So my next tangent line has to have a larger slope. So maybe something like this. And then if we just kind of follow that, and follow that, the only way for this to happen is if the curve itself has a shape like this. I realize I've done a kind of a crummy job there. I made those increase too quickly, but that's the idea. So f double prime being the derivative of f prime is what makes this work. You're looking at the rate of change for the rate of change. In other words, if you know that f prime is increasing, then you know that the slopes of the tangent lines get steeper and steeper as you go further and further to the right, right? They are growing. So from knowing that f is increasing and f prime is increasing, we can sketch a rough graph of f, and it is necessarily concave up, because as I go from left to right, the tangent lines have to be getting larger and larger in their slope. That's what it means to say f prime is increasing. I can look at one more little example like this. Let's assume that f is increasing and f double prime is negative. So since f double prime is since f prime is positive, again, f is increasing. Since f double prime is positive, that means f prime is decreasing. So the slopes of the tangent lines must be getting smaller. So again, I'll draw a graph just based on the tangent slopes. Again, I'll tick off some x values here. If f prime is increasing, then my first tangent line has to be positively sloped. Okay, so let's say my first tangent line here at 0 has a nice steep positive slope. Something like this. F is increasing, so my next point has to be above the first point. But f double prime is negative, so f prime is decreasing. So this next tangent line has to have a smaller slope, meaning something like this, right? Less steep than that. Again, if f is increasing, this next point has to be higher still. And since f prime is decreasing, because f double prime is negative, this tangent line has to have a shallower slope. And we continue like this, right? Shallower slope still. shallower slope still. So the only way a curve could do something like this is if it has a shape something like this, which is what we called increasing and concave down. So it's thinking about the rate of change for f prime and putting those two things together to see how it relates to the shape of f. So again, the big idea is that if f double prime is positive, then f prime is increasing, which means the tangent lines slopes get larger from left to right. And if f double prime is negative, then by the first derivative test, by the increasing decreasing theorem, then f prime is decreasing, which means that the tangent line slopes get smaller from left to right. So here you see the slopes of the tangent lines decreasing, and that forces the concave down shape. So that's why the second derivative tells you about concavity. All right, let's see, how I have you guys from 11 to 12:15, right? So we're a little bit over time. Let me give you one more definition and then I will let you go. An inflection point is a point on the graph of f where concavity changes, right? So a point where you go from concave up to concave down, or from concave down to concave up, is called an inflection point. A point where the concavity changes. These happen when f double prime changes sign. All right. So inflection points are points on the graph of the original function where the concavity changes from either concave up to concave down or concave down to concave up. If you're changing from concave up to concave down, that means your second derivative goes from being positive to negative. That would look like this. Something like this. So you see right here, my function goes from being concave up to concave down. This is the original. We are concave up here. We are concave down here. So this would be an inflection point. And you could go the other way. You could go from concave down to concave up. This. Right here, we have an inflection point because everywhere to the left, we're concave down. And over here, we're concave up. You hunt for inflection points the same way you hunt for mins and maxes. You're just doing it with f primed instead. So we're going to pick it up here on Monday. I'm going to give you guys a little homework set to work over the weekend, a little additional homework set to work where you're using the first derivative test and trying to find where f is increasing, decreasing, find mins and maxes. On Monday, I'll show you the second derivative test, and we'll talk more about inflection points. And then we're going to move on to graphing functions. We're going to go talk about section 4.5, which is how you can sketch really nice graphs if you know the sign of the first and second derivative. So I'll go ahead and let you guys go here for today. Monday, we're going to talk a little bit more about this stuff and then move into section 4.5. And that's it for me. I hope you guys have a lovely weekend.
I didn't get your videos from the 11 and the 13th video in the YouTube yet.
Let's
Did
see.
you have any other ways can send your video to me?
So the video from the 11th should be up. I uploaded that one. Let's see if this is working. Video unavailable. I don't know what the hell that means. All right. Yeah, it looks like YouTube, something went wrong with the video from the 11th. The 13th I haven't uploaded yet, but I will upload today. So I'll go back and fix this one and we'll upload these two today. So you should be good to go then.
Thank you.
All righty, guys. Take care. Have a good weekend. Stay safe. I'll see you on Monday.